Hi, everyone. Thank you so much for coming today. I want to thank Andrew and Neha, Wasim, and the organizers for inviting me. Generally, what I'd like to do is talk about my latest and greatest research on blockchain and distributed computing. But both Andrew and Neha asked me to say a few comments about building a new field, so I'll address that. So I want to start by inviting you all to October in 2 weeks in Zurich. There's the first ACM conference on advances in financial technologies. This is a sister effort to this effort, led by the ACM. And the goal is very similar. It's interdisciplinary research related to cryptocurrencies, blockchains, exchanges, and their applications. All right, so what I want to talk today about is a bunch of different things, so 4 different things. And if we'll have time, I'll be happy to get questions. And if you have urgent questions, then please ask me in the middle. I'm going to talk a little bit about one important thing which I want you all to do is follow the money. Then talk about the academic pillars of this new field. And finally, since this talk is called all about distributed trust, decentralized trust, I'll say what is decentralized trust. And eventually, I'll end by speaking a little bit about scalable Byzantine fault tolerance, which is, I guess, what I would like to do if I had talking about only about academic work. So as you probably know, there's a lot of money in this area. The cryptocurrency, last time I checked, market valuation was above $200 billion. There's a lot of people who made considerable amount of money in this space. And you're going to hear a lot of different speakers. And what I would recommend all of you to do is always ask yourself, follow the money, right? So people have either clear or transparent or not reasons to say what they're saying. There's a lot of money involved here, and you have to kind of figure out and understand who is talking and what are their motivations. In particular, the way I try to address this, and what I would recommend for building this field, is to focus on this notion of transparency. And so, transparency is basically operating in such a way that it's easy for others to see what has been done, right? And we're here in the first thing I want to talk about in transparency is transparency in funding and investments. And we're here in the Media Lab, and there's an elephant in the room. As you know, there's been horrible things related to funding. And I don't think that transparency alone would solve it. You have to have good moral judgment in addition to being transparent. But I think transparency can help. If you make incorrect moral judgment decisions, then transparency can help quickly or more quickly resolve these things. And so what I'm calling for is to have more transparency in this space. If you're personally invested in something, then people should know that, because that's part of maybe part of what you have to explain if you're in this field. If you are funded by some other entities, then you should also be transparent about it so that people know what are these economic forces on you. The second thing I want to raise, and I think is very important, is the transparency in conflicts of interests. I think this is also something that happens a lot in the academic world. There is a lot of different ties, and it's very important to understand the relationship between these different conflicts. There are people who work together or who do not work together or who have histories of collaboration and so on. And I'm personally against this notion of having kind of this binary approach of there either is a conflict or there isn't. If you work with somebody in the last 2 years, then you can't review a paper. And if it's 2 years and 3 days, then you can actually review it, and there's no problem. I think the right thing to do here is to be much more transparent and to have a much more mild view that explains all the different conflicts of interests. And here, I want to say that this approaches of anonymity and submission can sometimes actually hamper the effort to be transparent, because then people can say, well, I don't know where this paper is from. And then you lose kind of the mild conflict of interests that might actually be there. Transparency is also about doing good research. So there's transparency in mathematical results, which means that if you have a theorem, then it should be possible to actually devise a full proof out of that theorem. So it's not some sort of opaque statement that you're claiming, and then nobody can actually verify it to the detail. So I'm calling for transparency in that notion too. In systems research, transparency is also extremely important in my mind. In particular, I want to point out to the ACM efforts for artifact evaluation. And kind of they have 3 different badges. The first is just availability, so that whatever you're claiming your system does, there is some available code. The second is functionality, which is, well, this code actually runs and you can actually try and test it. But the most important thing, and this is kind of how the scientific method works, is reproducibility. It's the ability to actually replicate the experiments that you're claiming in your paper. And I think that without having a field that can actually do these repeatable experiments, we're going to get into papers that claim things about systems, and there's no ways for us to actually progress the field by verifying these claims and trying to compare them. Andrew mentioned transparency in peer review as also something that needs to be taken into consideration. I've seen places where, in addition to the paper, there is a public review by experts, and there's a public rebuttal by the authors of this public review. I think this is, again, something that we can learn from the open source community and from the developers, where in addition to having maybe a private review process, a peer review process, there is a public one. And finally, there is transparency in selection. So I want to thank the organizers for selecting me today. I'm privileged for that. And I think it's important for us in the cases where there is actually a selection process to be transparent about it and say, here's the committee that made this selection. Here, potentially, here's the criteria for which they made this selection about. OK, this is all about transparency. Now I'll talk more about kind of cryptoeconomic systems and blockchain technology and what I think are the academic routes and what we should try to follow. And back in 2007, I gave a job talk at Microsoft Research, and I had this slide. And this is kind of nice because this same slide actually fits to this research. So it's really about the 3 things that I'm most interested in. It's kind of the interdisciplinary area between these 3 amazing fields. So the first is economics, and roughly speaking, economics is kind of the study of how people react to scarcity, to scarce resources, and how they react to incentives. And there's kind of both a microeconomic game theory questions here and also a macroeconomic monetary theory type questions. The thing that economics is traditionally not really good at is evaluating protocols in software. It's more about looking at what people do. And I think this is where cryptography is kind of an amazing advance in humanity in general. And the way I can try to define cryptography is the ability to replace trusted third parties. Right? So if you have a signature scheme, one way to think about a signature scheme is that this trusted party is saying this message came from this person. Right? If you think about zero-knowledge proof, one way to think about zero-knowledge proof is to say, well, there's a trusted party that verifies this proof and says it's correct. And in general, if you're kind of in this area of cryptography, then these notions of universal composability and indistinguishability are actually extremely advanced mathematical notions that capture this idea of replacing trusted third parties in a very formal mathematical way. And I believe this is a huge breakthrough for humanity, this ability to replicate trusted third parties. And we're seeing advances in cryptography in the last, I guess, few years, which are amazing, both in terms of how new theoretical results are arriving and also in terms of how these theoretical results are becoming practical. So one of the things, for example, is that cryptography is now leveraging core ideas in theoretical computer science and complexity theory, and actually showing that these trusted third parties, you can not only replace them, but you can actually have them do work that is much less than what a trusted third party would allow you to do. And this is this idea of succinct proofs, where you can verify a proof in a very short amount of effort, even though presumably this trusted party had to do a lot of effort to check this proof. And so what cryptography is good at is these protocols. It typically has this good guy, bad guy notion, and it kind of doesn't think about the incentives. I think this is where the interdisciplinary connection between economics and cryptography joined in. And my personal expertise is in distributed computing, and I believe that, again, in this new area of blockchains and cryptocurrencies, distributed computing also has an important role, and it tries to capture the understanding of how we build large-scale distributed systems, how we deal with networks, and how we deal with failures, and how can we build systems that tolerate failures. And I really think that this interaction of these 3 things is key for this new field. So this was kind of my take, even back in 2007. But actually, my new take is that there are more things that need to be taken into account. And in addition to kind of economics, distributed computing, and cryptography, there's this new area I would call this notion of governance. This is not about on-chain governance, even though that's an exciting area to think about and so on. But this is really about how this whole field is related to political science, to public policy, to law, and really how governance affects the effect of the institutions, the social norms that we have. And I think that this interdisciplinary research has to kind of understand all four of them. So in particular, in the academic lens, what I would recommend here is, since this is in some sense a subfield of computer science, which is a subfield of mathematics, is that we maintain this high degree of rigor. So in particular, if you're doing theoretical results, you maintain high degree of mathematical rigor. If you're doing cryptographic work here, it should be at the highest rigor of cryptographic results. If you're doing game theoretic or economic reasoning, the same thing, and same thing for distributed computing. So we should have a very high degree of rigor. Similarly, if you're making legal claims, again, this should be at the highest standards. I think the biggest mistake that a sub-community can do is kind of drift away from that, and then kind of the other communities will basically not be able to understand and have a common language. In the systems research, this is even more important. I think this idea of reproducible results. I cannot stress how important it is. I've seen a lot of different papers claiming a lot of different things, and it's very hard to actually validate this and see whether this is true or false. I think in addition to just being able to be reproducible, we need to have comparable results. So it's not only that you build a system and you measure something, you need to measure it and compare it to previous systems, right? This is kind of the scientific method, where you make an hypothesis and you compare it to previous results and see whether your system is somehow better or breaks or does not break your hypothesis relative to previous work. I think we need to develop commonly agreed benchmarks in order to do that comparative work. In particular, we have to have common workloads, common ways to measure fault tolerance and security. And I think this is kind of an academic standardization effort that's very important for our community. All right, so I'm done with that. If there's no questions, I'm going to talk about decentralized trust. Good. So here's kind of an email that shocked me. So this is an email that Satoshi Nakamoto wrote in 2008. He said, "The proof of work chain is a solution to the Byzantine generals problem. I'll try to rephrase it in that context." So I learned about this email actually quite recently, maybe a few years ago. The way I learned about this email is actually through a New York Times article that Mark Andreessen wrote. He's a venture capitalist, a well-known venture capitalist. He said, Bitcoin, in this New York Times article, he said, "Bitcoin is the first practical solution to a long-standing problem in computer science called the Byzantine generals problem." And I remember in 2014, I read this and I said, okay, my work, I've been working in Byzantine fault tolerance for a year. You're joking, you're laughing. And this guy, he's a VC. He's writing something in New York Times, and he's saying something about my work. And I think he's completely wrong. And what I've learned actually is that there's a lot of truth in what he said. Now we know that actually Bitcoin or Nakamoto consensus underneath has major advances in Byzantine fault tolerance. It actually breaks this FLM lower bound and so on. So there's a nice I could say a lot of things about it. I won't today. But what I want to say is that actually it took me a while to realize this. And going back, I think he kind of realized, because you can see he used the same type of words that Nakamoto did in 2008. So really, my fundamental understanding here is that the core thing that Bitcoin got is the ability to solve Byzantine fault tolerance. And this is kind of one of the things that I've learned over time. And what I want to kind of say is I want to equate this idea of Byzantine generals problem and this notion of decentralized trust. I want to say this is kind of just a different way to say, or a modern way to say Byzantine generals. And here's a quote from the A16Z crypto investment thesis. And they're talking about blockchain computers. Blockchain computers are new types of computers with a unique capability as trust between users, developers, and platforms itself. I try to figure out, what does this trust mean in a more academically rigor manner. And kind of here's how I try to interpret this in terms of in notions of decentralized trust. And really, the way I see this is that this is a way to modernize the discussion about Byzantine generals problem or Byzantine fault tolerance. So in particular, the idea of decentralized trust is that you do not depend on a single monopoly power. Right? There's no centralized authority, but you try to somehow decentralize the decision-making into a group. In particular, this means that the properties of your system, liveness, safety, mutability, privacy, and so on, do not depend on one person or one monopoly, but actually in such a way that even if a small fraction of the people who have voting rights in your system are compromised, then the system still behaves correctly. Saying this in a slightly more formal way, we think about an adversary that can control a fraction of the voting power. And the properties we want from a system is, first of all, this property of liveness. What liveness means that good things eventually happen, right? That nobody is blocked from making actions. And this is true even if the adversary is trying to block the system. That's kind of the first property we want. The second property we want is this idea of safety. And I guess in the cryptocurrency world, this is about avoiding double spending. And if you're just interested in Byzantine agreement, then safety and liveness are just the two properties you want to do. And what I realize is that this is actually not the only thing that people are interested here, and this goes back to this notion of trust, where what people were worried about is platforms where there is some monopoly power to change the rules as the system continues to work. So we've seen this in different other cases where monopolies had some agreements with us, and then over time, say, change their privacy policy, or over time change the way they can extract value out of us. Right? Or change the pricing on us. So part of this idea of trust is also the ability to be immutable in the sense that if you want to change how the system works, you cannot do it with monopoly power. You actually have to have some sort of consensus of a large group of voters in order to make these changes. And I think this is part of the value of these new types of systems. And finally, I won't say a lot about it, but I think that privacy is also a very important aspect here. And again, the way I think about privacy is not kind of this extreme version of privacy, but it's the ability to have sub-type of guarantees, privacy guarantees, between the users of the system and the system, what the system provides, and make sure that whatever those guarantees are, those are exactly the ones that are being held. And so this is kind of my take on what decentralized trust is. But really what's missing here is who's managing this decentralized trust, because I mentioned here that there are voters. And really, the important question here is in this decentralized trust, who actually gets to vote? Who has power to make decisions? And if you think about it, we live today in a world where we all have kind of voting rights. But really, this is a new idea. So I think in France, this is something that happened less than 200 years ago, where they actually decided that everybody can vote. In fact, every male can vote. And the idea that women can vote is actually a very modern idea in society, right? This used to be not the case. So less than 100 years ago, in 1920, or slightly more than, exactly 100 years ago, the US decided that adult women can vote. And in France, it took even longer. And not everybody can vote. So for example, I'm not a US citizen. I can't vote here in the US. So, and there are people that live here and still can't vote. So the choice of who can or cannot vote is actually very important. And in computer science, this is kind of controlled by talking about the adversary power. And we try to limit the way that the adversary has control over the system by saying what fraction of the vote this adversary has. And this idea is kind of key to measuring the security of systems. And this is how do you distribute votes among the population. So one simple way is to have a closed membership group. Right? Let's say you have a Libra association with, let's say, 28 or 27 members. And each one of them has one voting right. That's one way to decide on a membership. A different type of membership approach is to say that if you have CPU, you have a voting right. Right? So every one CPU gives you one voting right. And maybe if you have a very, very fast CPU, that means you get more voting rights. And maybe if you have cheap electricity, then that gives you more ability to do voting rights and so on. And this is kind of the idea of Bitcoin kind of evangelized and now known as this permissionless model. And we're seeing new types of models, for example, this proof of stake approach, which basically says that if you have a token, that gives you kind of one voting right, right? So the more tokens you have, the more voting rights you have. So for example, Ethereum 2.0 is taking this approach where you spend 32 ethers and you get one voting right in this validation system. Tendermint has something similar and so on. And we're seeing new types of results that use, for example, the ability to claim storage as a voting right. And really, to me, when I think about these voting rights, it all kind of boils down to, well, all of these things are things that you can kind of buy through money. You can buy CPU through money. You can buy your coins through money and so on. So it really begs the question, are all these systems essentially building some notion of plutocracy? And what I'd like to, and are they actually leading to centralization? And one of the nice studies I like to quote is this 2018 study of Bitcoin and Ethereum, which basically showed that even though we think about Bitcoin and Ethereum as extremely decentralized, and yes, everybody can join, and it's completely permissionless, in fact, there's actually a very small group of mining pools that control voting rights, I think less than 15 at least at the time. And actually, there's a very small number of ASIC providers. You can't really try to do Bitcoin mining today with your laptop or even with your data center. You have to buy dedicated ASICs in order to do this. And there's actually very few vendors that do that. So again, they have a lot of monopoly power here. And so there's this claim that proof of work actually forces you to create centralization. It also makes people who live near very cheap electricity get more voting power. Right? Do we want systems where if I live in a place where the taxation is favorable for mining, then I get more voting power versus people who live in places where taxation is unfavorable? So it's not clear why these choices are the right in terms of spreading voting rights. And again, this argument that proof of work is wasteful. And so really this question to me is this big macroeconomic question of how do we change, or is it actually the case that the only thing that we can do is basically say that the way these systems work is the more economic power you have, the more voting rights you have. And this one open question really to me is how do you avoid monopolies in these systems? And how do you prevent briberies? How do you prevent somebody who already has a lot of power to basically buy votes? And the second type of question I have, which I don't have a good answer to, is how do you actually prevent this centralization, this rich get richer effect, where there's a small group of people that have a lot of monetary power that have most of the voting rights? And what I want to say here is that there's a difference, and I think there's a lot of confusion here between the notion of who has voting rights and what is the consensus protocol. So a lot of people say, oh, it's either proof of work consensus or proof of stake consensus. And really the way I see this is that proof of work and proof of stake are just means to decide who gets voting rights. Once you have voting rights, you can decide what type of consensus protocol you're running. So here's an example of different types of systems. And they have different types of voting rights and different types of voting protocols. And it's true that kind of Bitcoin has both proof of work and Nakamoto consensus. But you can mix and match things in many other ways. And I think part of the thing I'd like to do is have the right type of vocabulary where proof of work and proof of stake talk about who has voting rights versus what is the consensus protocol. That's asynchronous, synchronous, partially synchronous, and all the fun things that I'd love to talk to you about. And I won't have time today. Right, so now I'm going to talk, in the few minutes I have, I'm going to talk about scalable Byzantine fault tolerance and a little bit of the work that I've been doing in this area. Here's the slide from 2016. And this was kind of our early vision of how you build this decentralized trust architecture. We're using 3 different layers. So the bottom layer is consensus. You build a Byzantine fault tolerant state machine replication. And you can think about Nakamoto consensus as a similar thing. The middle layer is a smart contract layer. You can think about, say, Bitcoin script as a different type of smart contract layer. EVM is an example of a smart contract layer. And you're seeing different types of smart contract layer languages and execution engines appear. And finally, on top, the third layer is these distributed applications or decentralized applications that run on top of it. And this is actually not a new vision. This is something that's pretty old. This comes from research in Byzantine fault-tolerant state machine replication. And this is work that Barbara Liskov and her group did in the early 1990s. And this was developed extensively in the last 30 years. And the high-level approach of this Byzantine fault-tolerant state machine replication is this idea of a primary backup paradigm, where there's a group of nodes that replicate a state machine. In every view, there is one primary and a bunch of backups. And there's kind of a way to switch between the primaries, so to do this view change that moves from one primary to another primary to another primary. And what these systems have is these two properties. The first is that they're always safe, so there's no disagreement. And this is true even if the system is completely asynchronous and there's complete denial of service attacks. And the second is that when the system stabilizes, so when there is enough synchrony in the system, then it makes progress. And all of this is done under the assumption that an adversary can control less than a third of the voting rights, less than a third of the nodes in the system. So this is kind of the optimal bound for this scenario. And what I want to say is that this is the blueprint that we got from Barbara and even from earlier research. And you're seeing a lot of systems today take exactly the same type of architecture. And this is what we took in SBFT, and this is a scalable version of PBFT, this system that was built in MIT. And this was published this year in DSN. In particular, it uses new algorithmic ideas and modern cryptography to get a more scalable Byzantine fault-tolerant state machine replication system. So in particular, we use collectors to avoid quadratic communication. So what we found is that running systems that have a linear amount of communication is much better than quadratic at scale. So if you have 200 or 300 validators, this becomes very important. We've also found that you can replicate the collectors. So instead of running one collector, you can run a group of them. And then you can have fault tolerance between the collectors. Right? We're using more advanced or more modern cryptography in order to get smaller signatures and faster signatures. So this is kind of using BLS signatures to reduce proof length. In particular, one of the algorithmic advances that we did in SBFT is the ability to reach consensus in one round. So typically, Byzantine fault-tolerant protocols take 2 rounds to reach consensus, or 3 rounds to reach consensus. And here, this protocol is unique because it actually has a solution, a correct solution to do a 1-round consensus. So it's a very efficient, low latency protocol. And we've done this and added a correct view change protocol that works for this. And the important thing here is not only as a theoretical result, but this is also one of the first academic results that I've seen that has been rigorously tested and published in benchmarks that again, try to repeat the benchmarks that have been done in the past. And in these benchmarks, we've shown that in a wide area network for roughly 200 nodes, running real workloads like EVM smart contracts, we get roughly 2x the amount of latency and throughput relative to previous types of systems. And this work is now part of VMware's effort, and this is a work that we're doing, taking this and building an enterprise-grade solution that's based on SBFT, and this is a Concord BFT. You can look at it on GitHub. So I mentioned I'm part of VMware, and here's one effort that we're doing at VMware that's related to blockchain and using this type of technology. OK, so here's my conclusion. What I talked about 4 different things. The first is follow the money. Ask yourself, whenever you hear people talking, what are their motives? Where are they coming from? And as a field, I believe that the right solution for this is transparency, to increase transparency in a lot of different types of dimensions, and I mentioned them. I think that this field is really a combination of at least 4 important interdisciplinary areas that need to be combined together. And I urge all of you to learn all 4 of them and to discover how each one of these 4 can help you improve your work. I've talked about what I feel is this notion of decentralized trust, how it's a modern view of Byzantine fault tolerance that provides you liveness, safety, immutability, and privacy. I stress this notion that even if you have this idea of decentralized trust, always ask yourself, well, the group that's implementing this trust, who are they? Who are the people who get voting rights in this group? It's a very important question to ask. and then realize that the people who have voting rights is a different question than what is the voting algorithm, what is the consensus algorithm. These are two different questions. And finally, I talked about our systems effort, SBFT, and how we're trying to build something based on this idea of state machine replication and Byzantine fault tolerance. Right, thank you.
Thank you. Very interesting talk. I would just like to know why VMware is interested in SBFT.
So VMware traditionally provides infrastructure for IT. And we believe that part of the modern infrastructure, in addition to compute infrastructure, storage infrastructure, and networking infrastructure, is going to be decentralized trust infrastructure. So we think that will be part of what new computing will want, or new IT will be asking.
Thank you, Ittai.